Let's take an extra problem A. We have a semicircle of dielectric material, non-conductive, of radius A. As you see here, we have two portions. We have the left one, the red one, positively charged, and the right one is negatively charged. The charge density is equal to lambda. Okay, now we have to calculate the electric field magnitude direction at the origin due to the positive quadrant. So we have to find the electric field created by the positive quadrant. Okay. Let's draw. Okay, here we have this part is positively charged. So we are talking about only this part, only this one. In general, as you know, we have to take a small portion. We can say this one. Let's say here we have dq with a length equal dl, and we join this point to this point. Here we have to calculate at the point O that the total electric field created only by this part, the positively charged quadrant. As this is a positive charge, so dE must be directed like this. And here we have dE. Before, is this part is symmetric with respect to the point O? No, because if you take another charge here you have one, and here you have one, and you do delta E, you will not get two opposite components. Okay, this one is not symmetric. For example, let me do it quickly. Here we have dE. dE has two components. We have dEx and dEy, and this one also, let's say it's like this. We have dE. Here we have dEx and dEy. Alors, we don't have two opposite components. We don't have symmetric. In this case, we have to calculate. In this case, we have to calculate dE equal dEx plus dEy. These two components. Okay. We can eliminate this one. Okay. So here we have dEx, and here we have dEy. Let's say here we have an angle equal to theta. Okay, you can say this one equal to theta, or this one equal to theta, whatever. We will get the same calculation. Here we have the opposite angle equal to theta. Let's do the magnitude of dx. Here we have dx magnitude in the positive direction, in the direction of plus I. So we write dx plus I, and the y component in the negative direction, in the direction of dEy minus j. We have dx, we have dEy. To calculate the total electric field at the point O, we do the integration. Here you have dEx I minus the integral of dEy j. You know that dEx equal, let's take this triangle. Here we have, okay, this triangle. And here we have the right angle. dEx is the adjacent side. So we calculated by cosine. So dEx equal dE equal dE cosine theta equal dE equal K dQ divided by the distance between dQ and the point O, which equal to A square times cosine theta. Cosine theta. Okay. dEy equal, let's see in the triangle. Here we have dEy. It's the opposite side, so sine theta. dEy equal dE sine theta equal K dQ divided by the distance square times sine theta. We substitute dx and dy in the equation 1. So equation 1, E at the point O equal, we put K out, the integral equal K integral dQ divided by A square cosine theta I minus K dQ divided by A square sine theta J. You know that A is constant. If you move dQ on the quadrant from this one extremity to the other extremity, A must be constant. A doesn't change from here to here to here to here. A is constant. So we can get out A square. A square. So we can delete here A square, A square, and we put here A square and A square. Now we have to calculate dQ. You know that dQ equal lambda dl. We don't have, dl is not on the x-axis and not on the y-axis. So we keep delta L. Here, you know, dl is located between d theta. Here we have an angle equal d theta with a radius a. So, and here we have dl. dl equal a d theta. Okay, dl equal, so dq equal lambda, dl equal a d theta. We talked about this before when we have a the center like this, and this is an arc with length L, the angle theta, and the radius R. L equal R theta. If this length is small, we have dl. With a small angle d theta, we can say dl equal r d theta. So dq equal lambda a d theta. We substitute the value of dq here. So E at the point O equal K divided by A square. dq equal lambda dl. Lambda is constant because the charge is uniformly distributed on the object. We can put lambda out of the integral. Inside you have dl cosine theta I minus k lambda over a square. Also, we have dl sine theta j equal. So now we have two parameters. If you move delta L from here to here, theta will change and delta L position will change. So we have to transform delta L to d theta. Okay, it's important. You know that dl equal r d theta. Let me see here. dq. Okay, here we have dl. You know this, dl equal r d theta. We can substitute its value here. Okay, so we get q lambda divided by a square dl equal r, it's a, okay, the radius is a, equal to a d theta. We can write cosine theta d theta, dl equal a d theta in the direction of I minus k lambda divided by a square. Also dl equal a d theta. You can write a sine theta d theta in j direction. Also we can put a outside, okay, so we can get out a and put it here. We put a here and a here, and we can cancel a from here and a from here. You will have only a down. Okay, now let's put the limit. It's important now, as we have only theta parameter, we have to put the limit of the integral. You know that before I had this one, and the angle is here. If we move, let's say, if we move the angle here at this position, the angle equal to 0. Like this, the angle equal to theta. To this point, the angle equal pi over 2. So if we displace, if we move dq from one extremity to this extremity, theta will change between the angle equal to 0 at this point to the angle equal pi over 2 at this point. So we put the limit between 0 and pi over 2. Also, here we have the same between 0 and pi over 2. We do the calculation. Let's write here. Okay, E equal K lambda divided by A. We cancel 1 here and 1 here. We have A integral cosine theta d theta 0 pi over 2 I minus K lambda divided by A integral 0 pi over 2 sine theta d theta j. Okay, the integral of cosine theta d theta equal sine theta. Remember this one. So here we get equal K lambda divided by A. The integral of cosine theta is sine theta between 0 and pi over 2 I minus K lambda divided by A. The integral of sine theta is minus cosine theta. So it's minus cosine theta between 0 and pi over 2 and in the direction of j. Okay. Equal K lambda divided by A, sine equal to sine pi over 2 minus sine 0 I. Okay. We continue. Minus K. Okay, we can put the minus outside. We can put, or we can keep it as you like. Equal K lambda divided by A equal minus cosine pi over 2 minus cosine 0 j direction. Okay, is equal to K lambda divided by A sine pi over 2 is equal to 1 minus sine 0 equal to 0 I minus K lambda divided by A cosine pi over 2 equal to 0 cosine 0 equal to 1 minus term equal to plus, so here we have plus 1 j cosine 0 equal to 1. So the final equation of the electric field at the point O equal K lambda divided by A I minus K lambda divided by A j. This is the value of the positive part. You can say at O from the positive quadrant. Now let's calculate the magnitude of this part. So the magnitude of the positive quadrant equal, don't forget, this one is EX component and this one is EY component. So the magnitude equal EX square equal K lambda divided by A square plus EY square equal minus K lambda divided by A square. So we have A square plus A square. You have the same quantity. You have 2A square. Okay, you can say equal 2K lambda divided by A square. So it's equal to K lambda divided by A radical 2. Okay? So finally, E, the positive part, equal K lambda divided by A radical 2. Okay. About the direction. The direction of the E positive equal tangent minus 1, Y component equal minus K lambda over A divided by the X component equal K lambda over A. So we get here K lambda A. So you have the tangent minus 1, 2 minus 1. You will have minus 45 degree. You can do the calculation by the calculator, okay? If you see well, if you want to draw its value, here we have delta E. Here the angle equal to 0. Here the angle equal minus 45 for the total E positive charge with the angle equal minus 45 degree. This is the answer of the positive quadrant electric field created at the point O. Okay. Now I ask you to calculate, deduce, be careful here. We have to deduce you have to deduce the magnitude and direction of the electric field at the origin due to the negative quadrant minus Q. Without calculation, we cannot do the same thing. We have to deduce its value from the part A. Okay. Here, okay, we can okay, here we had E positive quadrant, which is at a angle equal 45 or minus 45 degree. We want to calculate its value, the value of the electric field created by the negative part minus Q. As the positive part and the negative part have the same magnitude, the same quantity of charge, so E positive and E negative created by this one must have the same magnitude. but we have to precise the direction. You know that this positive part will create a field at the point O in this direction because it's negative. Here we have negative. So it's like this. If we have here a positive charge, so it must be like this. Because the negative, E must be in this direction. Okay? Like the positive one creates E positive at angle equal 45. So this negative has the same shape. So it creates the same electric field, but in this direction. So here we can say E negative. So we have to say here E negative is toward the minus Q, located at the blue quadrant. Okay? With the same magnitude as for E plus. Okay? So E plus magnitude equal E minus must be equal to K lambda divided by R or A, we can say radical 2. But the direction of E minus, E for E minus equal, you know that E minus has the x-axis here and the y-axis here. Okay, so here and the angle must be equal to 45. We have E minus x is positive, E minus y in the positive direction. So as magnitude or R vector, E minus equal E minus x plus E minus y. Okay? And as magnitude, it's the same like E plus. And the direction theta for E minus equal to 45. Okay, this is about E minus. Now, I ask you to calculate the results of the electric field created at the point O. So we have to calculate the total electric field created at the point O from the positive and the negative electric field quadrants. As you see here, we have E negative and E positive. E negative has E negative X and E negative Y, and E positive has E positive X and E positive Y. Okay, they have the same magnitude, okay? So here we can say E positive X, and here E positive Y. Before we calculated E positive equal to K lambda divided by A I minus K lambda A square. No, A divided by A J. You know that this value is in the positive I direction. It's here. E positive X in the positive direction, but E plus Y in the negative direction. So as you see here, it's in the negative J. Okay. Now we said E negative equal the same magnitude, but look here. E minus has EX is positive and EY is positive. The two values are in the positive direction. So we can write its value here equal K lambda divided by A in the positive direction plus K lambda over A in the positive direction. This is E plus and E minus for E minus and E plus. The question is, we have to calculate the total electric field created by the positive and the negative. Okay, we can see E total. E total equal E total X, E total X plus E total Y. So here is a summation of these two vectors is equal to the summation of the vectors of the X component plus the summation of the vectors of the J component. For the I component, we have this one and this one. You get K lambda over A equal K lambda over A plus K lambda over A. And the Y components, we have minus and plus. We get minus K lambda over A plus K lambda over A. Minus plus equal to 0. We get the final equation of E equal to K lambda over A I direction. So it's normal. Look here. Here we have E negative. Here we have E positive with the same magnitude. So the total E must be in this direction with E total. Here we have E minus, here we have E plus. And E is in the X direction with angle equal to 0. Theta for E equal tangent minus 1 Y component divided by X component equal to 0 degree. This is the total electric field created by the negative and the positive quadrants.